Good morning. So, how are you all feeling about momentum? We're one lecture into this. We're going to do lecture 2 today. We did quite a bit at that last class. Now, I realize that these new concepts are just kind of get stacked one after the other, so make sure you're staying caught up. Don't fall behind. Make sure that you're staying caught up with everything we're looking at. And everything continues to be relevant, right? We've been making use of kinetic energy in this chapter, which is on momentum. And where we ended up last lecture, we had gone through this very traumatic derivation. I hope you guys have recovered from that. It was just one-dimensional collision between two objects, but we generalized it to where the two objects coming in were both moving. And that means that in general, after the collision takes place, they could still be moving. Now, we said that, in general, we have a before picture, we have a picture of what's going on in the collision, and we have a picture of the after collision events, and that during the collision, there are contact forces. In this case, it's contact. It doesn't have to be contact. We'll see this can be generalized also. But if it's contact force, then the forces are equal and opposite. And that means that however much momentum transfers into object 2, that's going to match the loss of momentum from object 1. So we can think of this as a literal transfer. This many units of momentum were taken away from object 1 and they ended up transferring to object 2 as a result of the forces that took place during the collision. Now, the derivation we did, and I'm going to go through this fast because we already did it, but we started with momentum conservation. So at this point, you want to stop and look at that and think about it. Why does that represent momentum conservation? And then this equation represents kinetic energy conservation. And that says we have two equations. That's enough to solve for two unknowns. Now, in most cases, those two unknowns will be the final speeds of the two objects. They'll tell us the masses, they'll tell us the initial speeds, and then we have to figure out what the final speeds are. Now, we lined up the equations and we went through the derivations, and again, I'm going to save that for last lecture. But we had reached the point where we had come up with the equations. We achieved our goal of coming up with equations where given the masses and the initial velocities, we could calculate the final ones. And that kind of medium difficulty. I mean, the derivation was fairly challenging, but they're manageable. I mean, there's not so much going on that we can't imagine plugging numbers in. And in fact, the example we ended with was that what would happen if instead of both objects moving initially, what if one of the objects was at rest? So we imagined object 2 being at rest, and that eliminated this half of the formulas. And then we talked about what happens in the extreme cases where one of the masses is much larger than the other. So we said that if we have a really, really small mass at rest and an enormous mass is coming by, that enormous object is really unaffected, in the limit of where the M1 is really small, in the limit where M2 is really small. M1 just barrels through, and then if it's elastic, object 2 will be pushed away at twice the speed. Now, what's the relative velocity in this case? And that would be 2u minus u1, which is v2 minus v1. That would say that, yeah, the relative velocity after matches the relative velocity from before. And then in this case, too, the relative velocities before and after match. The lower example was where M2 was really large. We said that's like a brick wall approximation. And a rubber ball comes in and hits it, bounces right back with the same speed that it came in with. Okay, those are the limiting outcomes for that example. All right, let's look at some more collisions. It says in this example we're going to imagine the same mass. Now again, they're using pool balls, and I always have issues with this because it's so nice. I know it's really nice to see these things hit, and people have seen these, and it's kind of engaging to think about, but we've got rotational motion going on, and that complicates things. But it's not a bad approximation, so we're going to go ahead and work with some of these examples. So we're going to assume we have some collisions that are elastic. Both balls are moving initially, but ball B, both balls are moving initially. That's in part A, and then in part B, object 2 is at rest. So it's the very same equations we just derived. And so what's going to happen here is that V1 then is equal to, let's see here. So V1 is equal to m minus m, so the two masses are the same. So that's what's changed. Let's go back and look at the more general equations. So in this equation, there were distinct m1s and m2s, and now what we're saying is the m1s and the m2s are equal. Now, if m1 and m2 are equal, then this term drops out, and this term drops out. And these terms are going to become 1, because I have two masses on top and two masses below, and the masses are the same. So that ratio will become just a ratio of 1. And so that's what's happened here. So we've got m1, m minus m goes away, and m minus m goes away. What we're ending up with here then is the velocity of object 1 coming out of the collision is the same as what object 2 came into the collision with. So they're exchanging velocities. In this example, they both have velocities, so that's still, we're still allowing for both to be in motion. They're going to come in, let's say one comes in at 5 meters per second, this one's going at 2, then the collision takes place. In the after picture, then mass 1 is at 2 and mass 2 is at 5. So they exchange velocities. Now, they're exchanging momentum in these other cases, but since the masses are the same, they're also exchanging velocities. They just switch. Now, what would happen if one is at rest? Well, if V1 is if the second object is at rest, then V1 would be equal to U2, but U2 is going to be 0 in this case. So U2 is equal to 0. I needed to get that in. So I need to write down the U's here. I'm just kind of following up from the previous slide. But U1 is equal to V, and U2 is equal to 0 because it's at rest. And so this is what's happening. So we really only have one velocity to think about in this example. So what's happening is I got one object at rest, it's got mass m, I have the same mass object coming in with velocity v, collision takes place, it's elastic. If it is elastic, then object 2 comes out with the velocity that object 1 came in with. So that's a special case where the masses match up. All right, so what about unequal masses? In this example, the target is at rest, so U2 can be set equal to 0. A very common practical situation is to have an object at rest and then a moving object comes in and strikes it. And we have to assume in this one that the masses could be unequal and that the collision is elastic. So derive equations for the velocities in terms of the initial velocities, and so this is what we did before, right? So reading through all of this, this is good. We already have taken a look at this, and we've kind of just determined what this is all going to be, and so we were looking pretty good. So if this is at rest, and this is coming in with velocity u, and that's the only velocity, then the velocity of object A and B afterwards will be given by this portion of the formula. And then we had solved for this. We said that if MA is much bigger than MB, that in the limit, the velocity of mass A doesn't really change. It leaves the reaction at basically the same speed, whereas the much lighter object, if the collision is elastic, bounces off at twice the speed of the initial object. Okay. So again, if this is this is a pedestrian and this is a car coming in, then the car comes in at 20 meters per second. The car could continue going at 20 meters per second after the collision, but the person is pushed, away from the collision at 40 meters per second. So in this example, we'll flip things around. The object coming in is very, very low mass. Object B is really, really lots of mass. And in this case, object B is basically unaffected. Object A, if it's elastic, then would bounce off that object and be pushed back in the direction that it came from at the same speed that it came in with. Now, they're kind of setting us up with this, I guess. So here is a nuclear collision, and the collision they're talking about, here's a proton. So here's a proton coming in. Here is a helium nucleus. So there's a helium nucleus inside a helium atom, and a proton is coming in. We're firing a beam of protons into a bunch of helium. And one of the possibilities is an elastic collision, where the proton bounces off the nucleus and ends up going right back where it came from. So the proton's mass, they're telling us, is 1.01 unified atomic mass units. Now, if you've taken chemistry or maybe some physical science courses, you're familiar with atomic mass units. Atomic mass units are defined for convenience when we're working with different atoms and when we're looking with different isotopes of different elements. On that scale, it turns out the proton has just a little bit more than one atomic mass unit. Protons and neutrons individually have a little bit more than one. And we'll talk about why that is in Physics 4C. So the proton coming in is coming in at 36,000 meters per second, and there is an elastic collision. Now, elastic collisions at the level of nuclei and atoms and molecules and things like that means that you've got the same particles coming out as went into the collision. They're going to have the same masses, and that means that there's really nowhere for energy to hide. Whatever energy goes into the collision, it's got to come out of the collision. There's no such thing as friction, right? It's not like at the molecular level, there's not friction between molecules. There are just individual reactions between molecules. So those conserve energy, specifically kinetic energy. So let's set this up and see what it looks like. Talked about it a bit. Let's see what this might look like. Now, as long as we're showing the protons and neutrons don't quite have the same mass as one atomic mass unit, and that's what the little u is, and that's a unit of mass, so we're not using kilograms. The protons and neutrons are so small, it's more convenient to define a different mass unit, and that's what we've gone ahead and done. So the mass on the proton, 1.0073 something something something. The mass of a neutron, 1.0087 something 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 something. The mass on an electron, now protons and neutrons are kind of the same particle. It's like the proton is the charged version, and the neutron is the neutral version. They're very, very closely related particles. But the electron is a fundamentally different kind of particle. So the electron has much less mass, by a factor of like 1,800 times less mass. And on the atomic mass scale, it comes in at 0.00055 atomic mass units. Now, a combined helium nucleus has a mass of 4.0015 atomic mass units. So that's the mass of a helium nucleus. These are the ones where the collision is taking place. Now, if you a helium nucleus includes 2 protons and 2 neutrons, and if you've noticed, the mass of 2 protons and 2 neutrons is more than the mass of a helium nucleus. That's because you're going to have to come back and take Physics 4C for that too, because that's where we're going to learn about nuclear binding energies. Nuclear binding energies actually affect the mass of the nucleus. The nucleus actually has less mass when the protons and neutrons combine. See, here is a proton by itself, and then over on this side, that's 2 protons and 2 neutrons combined together. But the effect of the nuclear binding energy is to reduce the overall mass of the system such that the mass of the system, the entire nucleus combined, is less than the 2 protons and neutrons were individually. Okay, which is kind of interesting. Anyway, we're in Physics 4A, so here we go. Here comes the proton. Here is the helium atom. I wanted to draw the whole atom. Here are the electrons that are spread all over. The electrons kind of take up most of the space in an atom. And then the nucleus is just really tiny. So the protons and neutrons don't take up much space. Here comes a proton in. It's going to go right through the electrons, and it's going to make its way to the nucleus and have a reaction there. Now, we're going to go back and use our formulas for an elastic collision. And what we'll do is we'll plug in, this is going to be M1. Okay, which of these numbers is M1? And it's this one. That's M1. Which of these numbers is M2? And it's this one. So this is M2, this is M1. And I'm just plugging these numbers in. The initial speed was given. So the initial speed was given as, there it is, 3.60, 10 to the 4th meters per second. Now, putting that number in for V0 and putting all the masses in says that the proton comes out with a speed of 2.15 10 to the 4th meters per second. So it came in at 36,000 meters per second. It bounces back at 22,000 meters per second. And what about the helium nucleus? Well, the helium nucleus is pushed forward at 14,000 meters per second. So that's, those are the numbers, using the formulas that we developed for elastic collisions, and they work for these nuclear reactions as long as the particle coming in is not traveling too fast. Then the classical formulas from Newton will work for this. Now notice that the relative speed of approach was the 36,000 number. So the relative speed as the 2 objects approached each other, 36,000. What is the relative speed of separation? And if I add these 2 numbers together, because they're headed in opposite directions, this is negative, this is positive, they add up to be 3.60 10 to the 4th. So the speed of separation matches. That's a good sign. That means we may have done the calculations correctly. And what was the effect here? Let's see, we took a lighter object and ran it into a heavier object. It wasn't extreme. Like the heavy object was maybe 4 times as much mass. And you can kind of see how much momentum transferred into the helium nucleus. So, you know, a fair amount of the momentum did transfer. Okay. And so, yeah, here's the details of that. Here, this is coming in at 36,000 meters per second, and then they separate still at that same relative velocity. Is this supposed to be V naught? It's not supposed to be V naught. Why did that get written as V naught? Should be V1 and V2. So, okay, so this is V1, that's V1, and this is V2. So V1, V2 on that side. I need to get that corrected. What about inelastic collisions? So we've looked a fair amount now at the collisions that are elastic. Now let's look at some inelastic collisions where the separation speed is not so big. Where does the energy go? For an inelastic collision, some of that kinetic energy is lost to thermal energy, or it could be that the energy goes into potential energy. So let's take a look at some different examples where energy gets converted into heat, into thermal energy, where energy gets converted, kinetic energy becomes potential energy, and then what about where we have an explosive collision where there's an addition of energy during the collision as it takes place? So a completely inelastic collision, that's what we first looked at, where they just stick together. All right, here are those 10,000 kilogram railroad cars again. So railroad car A is going at 24 meters per second, strikes an identical car B, that's 10,000 kilograms. If the cars lock together as a result of the collision, how much of the initial kinetic energy goes into thermal energy? So that's a good example. Here's something that's completely inelastic. Not all the kinetic energy is going to go away, but a good portion of it will. So with these two railroad cars, if they stick together, they're going to be generating thermal energy. Let's find out how much. Here's the setup for this. So here is the railroad car at rest. Here's the one coming in at some velocity. They stick together on the way out. We had solved for much of this. The two masses were 10,000 kilograms, and the initial speed of the first car, 24 meters per second. Now we had used momentum conservation to determine, and I hope this is abbreviated now because I'm hoping you guys are getting more familiar with this. So this is momentum conservation. We can solve for V. That turns out to be 12 meters per second. Let's do the energy conservation portion and find out, let's try and account for where all the energy would be. So the initial kinetic energy in the initial picture, 1/2 m1 v naught squared. Now, if both objects were moving, I would have to add their kinetic energies together. There's just one object moving, and its kinetic energy is 2.88 million joules, or 2.88 times 10 to the 6th joules. Now, after the collision takes place, I can still use the kinetic energy formula. I can still use kinetic energy as 1/2 mv squared. And so the mass now is really both objects together moving at the same speed. So I'll put in 20,000 kilograms to save a little space here on my paper. 12 meters per second squared. It turns out that it looks like half the energy's gone. Now, the 1/2 number is coming as a result of the masses being the same. But in any case, if the masses were different, we could still go through the same set of calculations and determine how much of the kinetic energy remains and how much of the kinetic energy is gone in the collision. And we lost 1.44 million joules of energy, kinetic energy, in the reaction. Now, energy is conserved in general. So where did that energy go? Well, it went into thermal energy. I'm going to use a big T for that. What does the thermal energy consist of? And the thermal energy would be the kinetic energy of the molecules, of the regions of the cars where the collision took place, probably. So if this came in and collided, then we're guessing wherever the collision directly took place, especially, those molecules are going to be heated up as a result of the collision. Those molecules are going to be moving faster. So it's kind of funny, but the large-scale kinetic energy, some of it's being converted into really tiny-scale kinetic energy. It's being converted into kinetic energy of the molecules. Okay, so that's it. That's where that energy ended up. And so we can do the energy bookkeeping. We started with this much kinetic energy, 2.88 megajoules, but after the collision, half of that had been converted into thermal energy, 1.44 megajoules, while 1/2 of the original kinetic energy remains as kinetic energy. So the energy bookkeeping is still really important. We have to be able to go in and determine where the energy is going. So here's another example of a completely inelastic collision. This is referred to as a ballistic pendulum. So what we do is, in ballistics, you fire weapons into some kind of an object, and then you can measure how much momentum was transferred into that object. So that's what we're doing here. Is we've got an inelastic collision takes place because the bullet is fired at this block, maybe it's just wood, and becomes embedded in the wood. And then what will happen as a result, this is a lot heavier than the bullet is. And so its speed is going to be much reduced. The bullet comes in at a really high speed. It's very difficult to measure what that speed is. So what we're doing is we're firing it into an object with much more mass. And then in order to measure how much momentum was transferred, what we can do is work in terms of the energy. So the energy that gets transferred will cause the pendulum to swing upwards. It's going to come to some height. So you can see that if we use the bottom of the pendulum as a reference, the bottom of the pendulum has swung upwards by a distance h. We'll look at the formulas and see how this is all working. I just wanted to point out, I'm not sure how this whole thing is constructed. I would think that this would need to be very sturdy. These can't just be strings. They got to be like metal rods or something. And then maybe there's some bolts where those can rotate back and forth. So maybe there's some kind of a pivot joint set up where it's pivoting from here and it's pivoting from here. Because you need something that would stabilize this. You know, if you fire a bullet into this block of wood or whatever it is, you're not necessarily going to get everything moving exactly in the forward direction. So if you hit this off center, there could be wobble sort of things going on. Anyway, just curious about how these are manufactured. All right, so what we're going to do is we're going to break this down into a couple of steps. The first step is the collision itself, and the collision itself, we can use momentum conservation. Now, we can't use energy conservation because kinetic energy won't be conserved in an inelastic collision. So what we're going to do is say, okay, let's use momentum conservation for the collision itself, and whatever momentum the bullet came in with, which is m times v naught, that's going to equal the momentum in the block with the bullet inside. Now, before the collision takes place, it's just the bullet that has momentum. But after the collision takes place, it's little m plus m, so there's going to be a new velocity. Now, this velocity only applies to immediately after the collision. It's only right immediately after the collision that we can set up the right side of this formula, because after the collision takes place, then the block ends up swinging upwards, right? So, and the velocity is not going to stay constant. So this corresponds to, this is before the collision, and this is immediately once the collision occurs. So the bullet's going to slow down and stop within that block very rapidly, and then right at that point, we can write this formula down. Let's see, the second step here then would be picking up from where step one left off. The collision just happens, the bullet is embedded inside that block, and now what we can do is say, okay, there is a certain amount of kinetic energy remaining after the collision took place. We can take that much kinetic energy and set that equal to gravitational potential energy, because this thing, it's a pendulum. It swings upwards. So what we were showing right here is, in order to work our way back and find out how fast the bullet was traveling, we need to measure little m, big M, and we need to measure h. And I think that's it. Okay, so if we know how high this thing swung and we know what the masses are, let's see if that's going to be enough. So here are the formulas. The formula for the momentum part, I went ahead and solved that, and says that the V naught, the bullet coming in, is equal to m plus big M over m times the velocity immediately after the collision. Now, using the energy conservation equation, so let's see, oh, here it is right here. So what we can do is we can take that kinetic energy and set it equal to this potential energy. Now, if I set those two equations together, or equal to each other, m plus m is going to cancel out. So the two m plus m factors go away, and if I solve for v squared, it's going to equal 2g with a factor of 2 added on. So this is my equation for the collision itself, and this is the equation for the swing, the pendulum swing, where we're using energy conservation. And combining those two formulas together, here are the formulas. V is equal to 2gh square root. V naught is equal to m plus m times m. We can take the velocity calculated here, transfer it over to here, and it says, here is the one fell swoop equation. It says that I need to measure the height, and I need to know the two masses, and I need to know the gravitational field, and that's enough. That's enough that we can go in and determine what the initial speed was for that bullet that was coming in. All right, and we've got a lab. So we have a lab too for ballistic pendulum measurements. All right, here we go. We are going to start looking at more dimensions. So we're going to be looking at more dimensions, and in particular two. I don't think, we're not going to do anything in 3 dimensions, but you'll get kind of the idea with 2. Conservation of energy and momentum can be used to analyze collisions in 2 or 3 dimensions. But they say this, unless the situation is very simple, the math quickly becomes unwieldy. It's a lot of algebra. And so we're going to take a look at a few examples here, just to get a feel of how this works, and then also conceptually to think about what's going on. But here we have a moving object colliding with an object initially, and I should point this out too. I mean, you know, there are two-dimensional problems in the homework, in the sample problems for the midterms, and the midterms too. So you do want to be able to do some of these two-dimensional examples. So we got a moving object. We're going to start in this example with something at rest. So here is something at rest. Here is something coming in. And what happens is there's a collision. As a result of the collision, object A ends up traveling at an angle. It's no longer confined to one dimension. It's not all traveling along the x-axis. So in that case, object A now has a momentum which has x and y components. Both x and y components of momentum are showing up. Well, object B is also then going to be heading off at some angle, and object B will also have components of x and y momentum. So what are going to be the rules then? So if I'm wondering, what are the rules for writing down equations to represent momentum conservation for these? Okay. So here's a problem here, making use of this. Actually, let's go back here and talk just a bit more before we head into that example. So in general, what we would say then is that I start off with momentum in the x direction. When I look at the after picture, which are these two objects here, the x momentum here and the x momentum here combined have to equal the x momentum coming in. So I'm going to write down one equation that conserves momentum in the x direction. Now, I've also got momentum in the y direction after the collision took place, but I didn't have any before. What does that say about the momentum in the y direction for objects A and B coming out of the collision? And since there was no momentum in the y to start with, the momentum that object A acquires in the y direction will have to exactly balance out with the momentum of object B. So that's going to be two equations. We'll have an equation that conserves momentum in the x direction. We'll have an equation that shows momentum conservation in the y direction. If we have an elastic collision, which we could, if it's elastic, then there would be a third equation. But if not, we won't have that. So let's take a look at the example. So the example here is, it's billiard balls, so we're assuming the masses are the same. So that's going to help simplify the problem quite a bit, if we assume the masses are the same. Both balls are observed to move off at a 45-degree angle relative to the x-axis. So what are the speeds going to be then? So what we're saying is, let's see, I am looking for any additional information. I think we've got it all. So it doesn't come right out and say this collision is elastic, but it also doesn't say it's inelastic. Let's check it out and see. What we can do is we can conserve momentum to start out with. So let's use momentum conservation and find out if we can if we can calculate all of the velocities coming out of the reaction, and then we can calculate the kinetic energies. But let's see how much we can work with on this. So here's my before picture. I've got all the momentum is in object 1, and it's exclusively in the x direction. All the momentum is here. There's an arrow there, or should be. Here's an object at rest. And then here's my diagram for after the collision. Now what we had said was, if these are the velocities, then what I can do is I can multiply by the masses are all the same, to get the momentum vectors. So I could write this diagram in terms of velocities, or I could write the diagrams in terms of momentum, and I can switch back and forth as needed. Now what I do need to make sure is that the momentum in this direction matches the momentum in this direction. And I need to make sure that these two momenta combined are equal to the original x momentum we started with. So here's what those equations will look like. So here's an equation conserving momentum in the x direction. Here is an equation conserving momentum in the y direction. So in the x direction, we have the m1 v naught. This is the momentum of the object coming in. And then what we're going to take on the other side are the cosine theta components. The cosine theta components of both of these, notice the way the angles have been defined. If I take the cosine theta component, that will give me the x portion. For the lower one, the cosine theta component will give me also the x momentum here. And so m1 v naught is equal to the x momentum of the two objects as they separate and come away. Now, both of these momentum are in what we're calling the positive direction. So those are going to add together. Now, in the y direction, we don't start out with any momentum at all. So what we could do is just call that 0, and then say in the after picture, we're going to have those sine theta components of momentum. Those are going to be the y components. Now they're in opposite directions. And so the angles that we're working with is to say theta 1 and theta 2 are both 45. If that's the case, then I've got to make sure that I get a minus sign put in by hand right there. So we've done this before, where we use the diagrams to guide us in putting a plus or a minus sign into our equations. So that's what we're doing here. We're keeping the angles simple by using 45 degrees, but since one of them is really kind of negative 45, we're going to let that minus sign slide through to the front where we can see it. It's always good to write your equations so you can see the minus signs, I think. Explicit minus signs are better than implicit ones. If I can't see the minus signs, I could get confused more easily, I'm going to guess. Now, another way we could have written this, notice we talked about a 0 over here. It could be we just set these two momentum equal, right? I could say this, m1 v1 sine theta 1 equals m2 v2 sine theta 2. There's enough symmetry here. I can look at the diagram and see that the two magnitudes have to match. So I could have just set those two expressions equal. Now, these were billiard balls, and they told us that the masses, oh, there it is, the masses are equal. So the first thing that's going to happen here is that the m1s and the m2s are going to drop out of all of these equations. The v naught, they said, was 3 meters per second, and the two angles match. So the angles also, I can just drop that down into theta. So let's see if we took advantage of all that. What we can do then is, let's see, is we let all the masses drop out of the equation, and then what we're left with are just velocities and angles. And since the angles are both 45 degrees, I just put the numbers in. Cosine of 45, cosine of 45, sine of 45, sine of 45. They're all going to be the same because it's 45 degrees. So they made this a little easier by picking some angles that are easy to work with. So here are the equations I came up with. The masses, you know, as we talked about, are gone. The initial velocity then needs to be equal to v1 0.707 plus v2 0.707. That's the cosine of theta. The y equation just turns out to be v1 equals v2. All right? Because let's go back and see where that came from. That's really useful. And what happened was they told us theta 1 equals theta 2 and m1 equals m2. Well, if theta 1 equals theta 2 and m1 equals m2, then v1 equals v2. So there was a symmetry between the masses and a symmetry between the angles, and so it wasn't so difficult to establish that v1's got to equal v2. Well, if v1 is equal to v2 in the equation up there, then I can write v naught equal to 2 times v1, 0.707, and then I can solve for v1. So v1 worked out to be 2.12 meters per second. And v2's got to be the same thing. That's what momentum conservation is telling us. So I've got the two speeds calculated, and you know, I always want to go back and check and see if that makes sense. What was the v naught that we started with? And the v naught was 3 meters per second. So what I've got is a billiard ball coming in at 3 meters per second. It hits another billiard ball. They both head off at 45-degree angles away from each other. And they're both traveling at 2.12 meters per second. So I guess that makes sense. It doesn't sound crazy. It sounds like a possibility. But there's a way to check and see if that does make sense. And I would say, let's look at the kinetic energies. You know, we talked about, is this elastic or is it not elastic? We should be able to go in and find out. So let's see how much kinetic energy we started with. And the kinetic energy we started with before the collision was all in object 1. So that would be 1/2 m v naught squared. Now they didn't give us a value of m, so I didn't plug numbers in. I just left it as algebra, and so or as an algebraic expression. So the kinetic energy that we start with is 1/2 m v naught squared. How much kinetic energy are in the two objects after the collision? Now, they're both moving at the same speed. They both have the same mass. So they're going to have the same amount of kinetic energy compared with each other. And so I can write that as 1/2 mv1 squared and 1/2 mv2 squared. And then substitute in, now I did this algebraically, so I had to substitute in 0.707 v naught. So I substituted that in for v1, and I substituted that in for v2, and then I squared it. Well, if you square the square root of 2, you end up with the square root of 1/2. You end up with 1/2 again. And so that's what the cosine of 45 and the sine of 45, those are square root of 2 over 2. That's the square root of 1/2. And we squared it and got the 1/2 back. And so what this is saying is object 1 comes out with half of the original kinetic energy. Object 2 comes out with half the original kinetic energy. And that says no thermal energy was generated. All of the kinetic energy is accounted for. None of the kinetic energy went to heat. Now, that would make that an elastic collision. This is an elastic collision. Well, that's something we were able to establish algebraically by going through and solving for V1 and V2 in terms of V naught, and then running through all of the kinetic energy equations. And I like these problems, I have to say that. So again, in terms of what could show up on a midterm, I like this problem. I'm not saying this one's going to show up, but could, something similar to this. Now, I think what happens, if I remember, I would have to go back and remind myself if this is true. If we have objects with the same mass colliding with each other, I think if there's a 90-degree angle between them, the collision was elastic, and vice versa. If the collision is elastic, then the combined angles have to add up to be 90. Somehow that sounds familiar. We could double check that with some looking at some other algebra. We're not going to go there right now, but that's something we could check on. So again, that was a very interesting problem to be taking a look at. All right, here's another example of kind of a two-dimensional collision. Again, what they're doing is same mass, so they're being very kind here. So a proton traveling at 820,000 meters per second, that's pretty fast, collides elastically. They just come out and say it's elastic this time. So this time they're not giving us both angles. So this is common too. In these collision problems, we have enough information that we're going to be able to solve for a couple of items. But they'll give you different information in the problems. They don't necessarily tell you all of the information. Like, they could give us the final information and ask how fast the original particle was coming in. I kind of like that problem too. In any case, in this problem, we know they're both protons. The masses are the same. The masses are going to drop out of all the formulas because the masses are the same. The speed, there's an initial speed coming in, and then we know one of the angles to be 60 degrees. Is that right? Okay, they're saying we don't know which protons is a proton, but one of these angles is 60 degrees. We've lost track of which proton is which proton. And then they're just asking about the second proton and what will be their velocities. So I don't think the velocities are going to match this time. I don't think the angles are going to match. I'm curious if angle B is going to be 30 degrees because it's elastic. Let's go find out. So here's what it looks like. Very similar to before, the diagram at least. The 60-degree angle for theta 1 and the initial speed, and we're told that it's elastic. So let's write down all of the information that provides for us. First of all, there's a momentum in the x, and there's a momentum in a y. Now, for the momentum in the x, that looks exactly like the formula from before. For the momentum in the y, I just went ahead and set the two momenta equal to each other. I didn't do a 0 on the left side. We talked about doing that. This is equivalent to what we did before. Now, I've got a third equation, and so I'm going to write down, I've got two momentum equations, but I also have a kinetic energy equation, because they said that the collision is going to be elastic. So I wrote that down. Now, remember, these are two protons. So what happens to all the masses? And the masses will all go away. They're all going to factor out. I can just cross out all of the m's. Let's see where that leads us. And so once I've crossed out all the m's, this is what the momentum examples look like. Now the kinetic energy example is, this is not kinetic energy, sorry. So these are the momentum. We haven't used, where's the kinetic energy? It's down here. So I'm just working with these two right now. And what I'm going to try and do is this. Eventually, I want to match up with the kinetic energy formulas. And the kinetic energy formulas are going to be squared. So the kinetic energy formula tells me that once I drop off the 1/2 m, V naught squared is equal to V1 squared plus V2 squared. So those are going to have to be equal to each other. Now, from momentum, what we've done is, this is a bit of an algebraic trick. We've used this before, I guess. What I'm going to do is, I'm going to eliminate theta 2 right now. I'm going to come back and solve for theta 2 later on. So one way of eliminating theta 2 from these two equations, see, I've got like two equations, but I have so many unknowns. I don't know V1, I don't know V2, I know theta 1, I know V naught, but I don't know what theta 2 is. So I'm going to eliminate theta 2 by solving the first equation, this one up here, solving for V2 cosine theta 2 and squaring it, and then I'll take the second equation, solve it for V2 sine theta 2, and I'll square that, and then I'll add these two together, and the sine squared and the cosine squared will add up to 1, and that will cancel them out. And that's kind of a standard algebraic trick for dealing with equations that have sines and cosines in them, if you want to eliminate the angle. So that's what I've done here. Now that means that when I take this equation, solve it for V2 cosine theta 2, and square it, I'm going to get V naught squared, I'm going to get V1 cosine theta 1 squared, and I'm going to get a cross term that's minus 2 V naught V1 cosine theta 1. So that's what I ended up with. And then when I square this one, I just get V1 sine theta 1 squared. That one wasn't so hard. When I add up this side, I am ending up with V naught squared. Now these two terms will add together and give me a V1 squared. So a V naught squared plus a V1 squared, and then I've got this cross term over here, 2 V naught V1 cosine theta 1, that's also here. So what I've done is I have been able to solve for V2 squared using my two formulas for momentum conservation. Now, I'm going to take this entire expression, see that whole thing I solved for, and I'm going to substitute it in right there. So this whole thing goes in, and so this then becomes, well, the V1 squared is still there. But when I make that substitution, I now have a V naught squared. I have an additional V1 squared, and I have a minus 2 V naught V1 cosine theta 1. So that's what we've come up with. Now at this point, we've used all our formulas, so I hope we're going to be able to solve for V1 and V2. So what we were able to do here is cancel out the V naught squareds on both sides. add the two V1 squareds together, move those on opposite sides from the two V naught V1 cosine theta. That's what that reduces down to. I can cancel the 2's on both sides, and then I can take a square root and, or I can cancel out a 2, and then cancel out the factor of V1. And look, that's what we ended up with. So what went into this problem again? Because I want to know what this formula applies to. And what we assumed in the problem was it was two objects of the same mass, they were protons, and kinetic energy was conserved. It was an elastic collision between two objects with the same mass, and it was two-dimensional. So this is what we're going to find then, is that V1 is equal to the objects, the masses, the speeds, the velocities of the two objects are going to be given by V naught cosine theta 1 and V naught cosine theta 2. So I boxed those because they looked kind of interesting to me. And then let's see where this leads us. So first of all, the V1 was equal to V naught cosine theta 1. I know all that information. They gave that to me. So that says that V1 is equal to 0.500 V naught, and that is going to give us, they gave us an, oh there it is. So this is what we found out. I'm boxing the stuff that I think is important. The initial velocity they gave us was 820,000. So object, proton number 1, is going to come out of the reaction at half that speed, which is 410,000 meters per second. Now, what about velocity 2 then? So what I did here is I switched the formulas around from the previous page. So you can see the algebra does get, I don't know if it's unwieldy yet, but it's headed in that direction. So what we've got here then is we're coming back to the equation that we worked from here, the V2s. So I've got a V2 squared here, and what we're saying now is we now know V naught squared, we know V1. So I can plug the V1 in and solve that, and I can still solve it algebraically. So that's what I did. I took the elastic formula. So here's the V1 formula. This is the elastic formula from kinetic energy. I think that one's, I could have gone to either one. Let's see. So I'm actually working from this. Okay, so I solved for V2 squared equals V naught squared minus V1 squared. That's the one I used. And that is right here. So this is a kinetic energy formula. And I put in the V naught squared. But then what I did was I substituted in the expression that we discovered for V1. And what I ended up with was 0.750 V naught squared. So taking the square roots, I got V2 is 0.866 times V naught. That's the square root of 3 over 2. So V1 is half of V naught. V2 is square root of 3 over 2, 0.866 V naught. And when I solved for theta 2 from the equation, I ended up with 30 degrees. So this one was given, this one I solved for, and cosine, here's the cosine of theta 2 is V2 over V naught is equal to that 0.866. So it worked. I think that's a real thing here. If I have the same mass and kinetic energy is conserved, then these two angles combined will always add up to be 90 degrees. All right. So that one was more involved. We could go back, now that we have the velocities, we could go back and double check and make sure that the kinetic energies really did combine. Okay, so anyway, what do you think? That's a challenging problem, right? That's got a lot of stuff going on in it. It's also, I hope, it's also kind of fun to look at some of these more challenging problems. So I think what I'm going to do here, let's see. let's go through this. We just looked at all these two-dimensional examples for momentum conservation. So collisions in 2 or 3 dimensions. Identify the system. If it's complex, subsystems may be chosen when one or more conservation laws apply. Is there an external force? Boy, I'm not sure if this is the this doesn't necessarily describe the. They're talking about external forces coming in, and so I guess it's a checklist. So like in the previous example, the system we're looking at is just a couple of protons. Now, the system could be more complicated because we could say, well, it's 2 protons, but the Earth is there, so maybe there's a gravitational effect. Or, you could start adding other things in. And what we've done is we've ignored the outside objects and claimed that during the collision itself, the external forces like gravity were small. It was a small effect. So the proton running into another proton can be treated as if it were isolated. Now, once we've done that, once we've determined that it's safe to ignore the outside forces for the particular problem, then we drew diagrams of initial and final situations, and we clearly labeled all the momentum vectors, and we set up a coordinate system that would work well. Okay, once we've done that, then we wrote down the momentum conservation equations, and then if the collision turned out to be elastic, and how do you know if a collision is going to be elastic? And more often than not, that comes from somewhere in the homework problem or the midterm problem where it says, assume an elastic collision, right? Or this collision is elastic. So if the collision is determined to be elastic, then I've got one more equation. I can throw in one more equation. And then this is pretty funny here. Step 7 is just one word. It says solve. And what we've seen with these two-dimensional problems is, God, it can be a lot of algebra, right? The algebra can get to be pretty complicated. Going back and solving 2 or 3 equations, trying to find 2 or 3 unknowns among those equations. And then at the end, don't celebrate too quickly. Go back, check your units, make sure the units match up at every step, and check and see if your final results are just sensible. If you've got objects coming out of the reaction that are going a million times faster than the objects that went in, maybe you want to go back and check calculations. So check things along the way. That is always a good idea. So we're going to move on from the pure momentum portion of this. I think we're going to wrap things up for today here, but where we're headed now is to look at what's called the center of mass. We've referred to that before in the course. Here's an object. Gravitational forces are acting on every part of this object. Is there one location that we could consider to be kind of representative for all the mass of the object, and that's the center of mass. And so we'll come in and we'll look at methods for determining where the center of mass would be for a particular situation. Let's actually try just a bit more with this. Let's see what else we have. Some of the interesting features of the center of mass is this. Once we've identified where the center of mass is for an object, and it's going to be somewhere in the central region of the object. Now we're going to be more specific mathematically as to how that's determined. But once you identify where the center of mass is, you can follow the center of mass through this trajectory, and the center of mass of the object is going to be following the formulas for projectile motion, right? So remember we looked at projectile motion way back in chapter 3. And that's the path that the center of mass is going to be taken. Now, what this second picture is showing is that in this case, the diver decides to rotate at the same time. So if the diver is rotating at the same time they're traveling what's called translationally through the trajectory, the center of mass is that point which continues to follow the projectile motion trajectory. So that part is unaffected. Okay, so we'll stop there. If you guys have questions, stop by. We'll start out with this in the next lecture.